Hello, good morning, everybody. We are the FADS research class. I'm James McCullough.
I'm Catherine Weber.
I'm Harrison Tebo.
I'm Lulu Wright.
I'm Aiden Hare.
I'm Bella Pedrassi.
And our project this semester was about biomass accumulation around fish aggregation devices in the Exuma Sound. So FADs are known as fish aggregation devices, and a FAD is basically any object in the ocean that attracts fish. And throughout history, fishermen have noticed that fish are gathering around these objects, so they use this to their advantage and use this to increase their catch rates around floating objects in the ocean. On top here, we have a picture of a natural drifting FAD. It's a log in the ocean. And then on the bottom, there is a picture of one of our two FADs here at the Island School. We have a north and south FAD, both in the Exuma Sound, which is also in the pelagic zone. And it's made out of two steel buoys and connected to line which goes down 600 meters and anchored by a 3-ton block of concrete. So there are some issues with FADs around the world, and one of them is that they are non-selective. This means that FADs attract not one specific species, but any fish that are around the object. And this can cause problems when fishermen are using FADs to increase their catch rates, and they're, for example, dragging their nets around the FADs to catch fish, and their nets catch everything in the area, and this can include endangered non-target species such as turtles or dolphins. Also, there are about 100,000 estimated new FADs to be placed annually. And one of the main problems with FADs is that there are little to no regulations on these objects. So there's no regulations to who can place them, how many can be placed, and where they can be placed. Lastly, it is important to know that here at the Island School, we do not use our two FADs for fishing as a fish tool, but instead as a scientific platform to study migratory paths of pelagic species, since they are not restricted to one habitat. So throughout our semester, we have been focusing on 3 main research questions. The first is, how do FADs affect the spatial distribution of biomass? The next one is, how do organisms behave around the FADs? And lastly, how does organism succession and colonization occur around the FADs?
So one of the main ways that we're trying to answer these questions is through camera surveys. We look at the colonization around the FAD, so what species are coming to the FAD, when they arrive at the FAD, and the size of the group that they're in, and specifically association versus aggregation. So it's really important to notice where around the FAD the fish are. Aggregation means that a fish is within 30 feet of a FAD or 10 meters, and they spend the majority of their time living there. And association is usually larger predatory fish that are outside of that 30 feet. We also look at succession, so how the group of animals that are living around the FAD changes over time, and specifically predator-prey relationships, so if the prey come first and then the number of predators that come and how those two are connected. And then the spatial distribution of species, so we have cameras that point up looking at the surface, down looking at the FAD rope, and then upstream and downstream into the current and out of the current. And so through those cameras, we can see if there's only fish that are beneath the FAD or only fish that are above the FAD and how different species are interacting with the FAD. So we drive out to the FAD usually once a week to place these cameras. On the diagram, you can see we have 2 different camera mounts, one that has the upstream and downstream, and one that has the down. So once we get to the FAD, we immediately do a snorkel survey, which is just counting the fish that are in the water. And we have to do that reasonably quickly because the fish that are right there will swim away as soon as we get in the water to a depth where we can't see them. And then one of our research advisors will dive down to place these camera mounts on the FAD. And they record for about 1.5 to 2 hours, and then we will retrieve them next time we go to the FAD, bring them back to the lab, and then perform video analysis on them. So this is only a graph for 2 of our many camera surveys, but the x-axis has all the different camera angles, and the y-axis has the species count. And this is significant because for these 2, all the species were the same numbers at all the different camera angles, which shows us that the majority of fish are surrounding the FAD and not being in one place. And then the average amount of fish seen at the FADs, both of those same days. And this is significant because there's a lot more fish on the down angle, which we infer to mean that there are a majority of bait fish living underneath the FAD and feeding off of the algae that live on the rope.
All right, to continue to address the question, how does biomass accumulate around FADs, we decided to supplement a sonar survey alongside our camera survey. The reason behind this is that we wanted a deeper insight into what's going on in the pelagic zone. The sonar we have is a vertical echo sounder, and it's being lended to us from by Dr. Matthew Witt from the University of Exeter. It's a vertical echo sounder, so it's much like your average fishing finder, and like your average fishing finder on your fishing vessel. So it sends out a ping of sound energy every second at 96 kilohertz into the water column, and the sound energy reflects off of anything in the water column. This can include the sea floor, some fish, or some sargassum. Then the sound energy is then reflected back towards the sonar, and the sonar is then able to determine the distance and density of the objects in the water column. So the sonar gives us a value called NASC, which stands for Nautical Area Scattering Coefficient, and it's essentially a proxy for biomass in our project. Okay, so sonar methods. We deploy the sonar on a weekly basis, and it can be either in the day or during the night, and we drive the boat with the sonar towing behind us around 10 meters behind us, and we tow in a radial star pattern. With the FAD being in the center of it. Here you can see what a typical sonar graph comes up on our computer. Here you can see the red represents the sea floor, and these green bands represent biomass.
We were curious to see how biomass accumulation changes depending on location and time of day. Using all of the data we collected this semester from our surveys, we tested and found that there is no significant difference in accumulation around the FADs dependent on location or time of day. However, when we were looking at these 2 graphs, the top one being from nighttime and the bottom one being from midday, we determined that there is a variance in depth of accumulation, not in time. What this means is that during the night, most of the biomass accumulates 50 meters and above, versus during the day, it's around 80 meters down. This is due to the Deal vertical migration, which is a nightly migration in which fish that live further down in the water to avoid predation during the day rise during the night to feed on phytoplankton. These are 8 scatterplot graphs representing all of the transects we took this semester. Initially, we anticipated seeing a nice bell curve that peaked over the FAD and faded out towards either side. However, what we ended up with was a large cluster of dots on one side and a small bump in the center. The cluster on one side is due to the wall effect. At the beginning and end of our transects, we sometimes drive over the wall where the continental shelf drops off into the pelagic zone. There is a higher abundance of life there, giving us a higher NASC value resulting in this cluster. The small bump is more concentrated. We believe that from our visual surveys and our camera surveys that fish tend to aggregate really close to the FAD rather than associating further around it, resulting in the concentrated bump rather than the large bell curve. This is a zoomed-in version of the last 8 graphs, except that for this one, it takes the full 2 kilometers of the transect, but only goes down to 250 meters. For this one, we were curious about how association changes with depth. What we determined by running a couple of tests was that after 150 meters, there is a significant difference in association with the FAD, meaning that as we get deeper and deeper, there is less and less association with the FAD.
Light trapping is another method we use to understand how biomass accumulates around the FAD, and this is done exclusively at night, and it adds sufficient information to our sonar data because unlike the sonar data, it tells us which species and the biomass accumulation while the sonar data only tells us the biomass accumulation. And so the reason we use lights and light trapping is because it acts as a beacon in the dark, so organisms will swim towards it because they're just naturally drawn to it. And we have two methods for catching organisms. One is a quadrifoil trap, which catches organisms up to 5 millimeters, and the other one is a tube and PVC trap, which catches organisms up to 3 centimeters. And the quadrifoil trap uses one central tube with glow sticks in it, surrounded by smaller tubes, and organisms will swim in between the smaller tubes towards the central one and get caught in a trap. And then the tube and PVC trap uses a funnel with lights behind it, and organisms will swim through the funnel towards the lights and get caught in a net. And so here is where we place the light traps. So we have 3 locations, one on the FAD, one 500 meters away from the FAD, and one 1,000 meters away from the FAD. And at each 3 of these locations, we set 4 light traps at 4 different depths. One at 10 meters, one at 200 meters, one at 400 meters, and one at 600 meters. And so here's the data we've gotten from that. We're measuring light trap catch rate per hour, so the catch rate of organisms per hour. And going from left and right, it represents the increasing depth of the of the light traps we've placed. And so on the very leftmost bar, as you can see right there, the reason it has such a high catch rate is because of the Deal vertical migration, and also because at around 10 meters on the FAD, that is where the actual FAD itself is, the buoy structure. So it makes the most sense that organisms would be aggregating at this depth. So here are some of the catches we've had this semester. We've caught a shrimp, a juvenile Atlantic flying fish, and a baby octopus.
So our camera surveys and fish counts have allowed us to look at how fish aggregate and associate around the FAD. And what we've noticed is that smaller bait fish, such as almaco jacks and unicorn filefish, will aggregate very closely to the FAD, versus larger game fish like mahi, wahoo, and barracudas associate within that 10-meter radius around the FAD. We're also looking at how the succession of fish changes over time. And then our sonar surveys and light trapping data is allowing us to look at how biomass accumulation changes around the FAD, especially over time. All 3 of these different methods are allowing us to further answer the question of how fish in the Exuma Sound interact with FADs, and then how FADs impact the larger pelagic ocean. These are our citations. Thank you to everyone who helped us with this project, especially our research advisors, Sam and Eric. And Eric is currently in Scotland analyzing our sonar data while pursuing his PhD. Are there any questions? Yes.
Since you guys said there's no regulation of these FADs from a marine ecology standpoint, do you see them more as a detriment, or are they beneficial in the commercial fishing industry?
It's really just relating to how these commercial fisheries are using them. So whether it's used responsibly or whether the power is abused, it all depends on like the methods that these different fisheries are using, like whether they're fishing just specifically for a certain species or just throwing nets in and pulling up anything they can catch. Yes.
Why do fish accumulate around the FADs? Is it just the algae on the device itself, or are there other reasons?
So the question was, why do fish accumulate around the FAD? There's a few different hypotheses. Nobody actually knows exactly why. One of the main ones is that mouths of rivers are places where logs accumulate, and then lots of nutrients will be there, and so fish have adapted to think that like logs or things floating in the ocean have nutrients around them, and then the fish will come to those and eat the nutrients. And so even if there aren't nutrients, the fish will still think that and come to them.
When was this FAD deployed, and do you have succession data as to what fish or types of species arrived first and
Okay. The question was, when was the FAD deployed and do we have succession data? I don't know the exact date of when it was deployed, sometime last year. And there has been a few semesters that have done work like this, so there are Sonar surveys from past semesters and other surveys that have added to the succession data, yes. Any other questions?